This is Unit 3. This is Chapter 4. So Unit 3, Chapter 4. Okay. And I said it was Newton's what? First law. Does anybody know Newton's first law? Nope, it's not gravity. What goes up must come down. Nope, that'd be a gravity thing. Nope, you're close. Okay. Nope, that's the equation. That's the second law.
Is it like for every force is an equal and opposite?
For every force. Nope. What was that, Nikira?
I said that if there's an object in motion, it stays in motion.
Okay. An object in motion stays in motion. An object at rest stays at rest unless a force is exerted on it. Okay, now this was the example I was going to show you guys. Okay, here I have a baseball that is what? At rest. Now what's going to happen when I walk that way?
It's going to roll.
Why does it do that? Why does it do that? What'd you say? It's not air resistance. Okay. But it's not doing it now. Why is it not doing it now? It's against something, right? What's it against? The clipboard, right? So if I have it on the clipboard, and there's this little part of the clipboard where if I move the ball with the clipboard this way, what happens? Oh, that's kind of cool. What happens? If I turn it around and do the same thing, I'll try to hold it level. Okay? What happens? It rolls. Right now, this baseball has seams on it, which kind of make it difficult. The reason I picked the baseball and not tennis ball is the baseball has a little more mass. And that'll show up with later. Okay? If I go this way with it, right? It moves on me, doesn't it? Why doesn't it work this way? Someone said something a second ago. The what? Whoa. What'd you say, Derek? Good. This little piece in the clipboard is stopping the ball from moving, right? But if I go in this direction where the little piece isn't behind the ball moves, right? This little piece applies a force, right? That little piece applies a force. So what happens to the ball? It was at rest, and now it's in motion. But if I go the other way where the little piece isn't in the way, or if I flip my clipboard over, is there anything to apply a force? No. So the ball wants to do what? Wants to stay where it's at, right? The ball wants to stay right here. Okay? Does that make sense, guys? Does that make sense?
What about if you tilt it? Wouldn't it fall over?
Well, if I tilt it, then there's unbalanced forces. Because when I tilt it, now what's unbalanced? Gravity, right? My normal force is perpendicular to my surface, which is this way. Okay? Gravity is still pulling down. So will those two balance each other out if I have one going in an angle and one going down? No, they won't balance out. So that's why it falls. But if I hold the surface perpendicular, or parallel to the ground, sorry, my normal force is up, gravity's down, they balance. Okay? And that force is 0. Okay? Now I start walking, what happens to the ball? It rolls back, right? Does it roll in the same direction or the opposite direction of me walking?
This way.
Opposite direction of me walking, right? Because it wants to stay at rest. Okay? Anybody ever having this on the lunch line? You have an apple sitting on your lunch tray, right? And you're walking, you stop. And that happens? Yeah? Why is that? What? Because the lunch lady hates you. No, it's not it. Okay? Why does that happen? Apples are not your friends. No. The apple wants to stay in... No, if I'm walking, the apple wants to stay in... Motion. Right? So when I stop, the apple keeps going. Right? And it falls off my tray. Unless you have one of those trays that have the lips on them. Whoever designed those either was a physicist or got sick of their apple falling on the ground. Okay? So I bet the trays initially were flat because they're easier to make. All right, any questions? All right, so what's Newton's first law? And object There's a commercial that tells us this. I would play it, but I think it's inappropriate. Well, not inappropriate, but for a weird medicine that we don't want to talk about in class. Okay. So an object, and you can find it later. All right, an object. I can't remember what commercial it's for. It's either for one. Yeah, we're not going to go into it. Now we're getting into the reason why I didn't want to show the commercial during class. All right, an object in motion.
Does it rhyme with?
No, just don't worry about it. An object in motion stays in motion. Right? And what's the rest of the other part? An object at rest. Oops. Spelled anio. An object at rest stays at rest. Is that it? Unless the force what? Is exerted. Force acts on it, right? Okay. The way the law says it is unless an outside or an object in motion stays in motion, an object at rest stays at rest unless acted upon by an outside force. Okay. Unless acted upon by an outside force. Now, some of you are hearing this and thinking we're going to go outside now, aren't you? Okay. No, we're not going to go outside. The reason why it says acted upon by an outside force, okay? Because my baseball on my clipboard, it always says force is acting on, doesn't it? Yeah, what forces are acting on right now? Gravity and air resistance. Not yet, it's not moving. Gravity and the clipboard. The clipboard provides a normal force, right? So the ball itself initially, stay there, has a normal and gravity. And how are they related to each other? They're equal, right? Now, when the ball was on the clipboard like this, with the little clippy thing over here, my velocity went that way. What happened to the ball? The ball went this way, didn't it? Right? But when I had the little clippy do on this side, and had the ball staying here, and my velocity is that way, which way did the ball go? Same way. Maybe we should change to acceleration. I don't want to confuse you guys. Why did I change to acceleration? What does acceleration indicate? Change in motion. Force, right? Okay. Which way did the ball accelerate? When the clippy do is like that. That's a technical term, clippy do. Okay. Which way did the ball accelerate? Do I need to do it again? You're probably saying it didn't accelerate, right? It moved with me, didn't it? Right? So I'm accelerating this way. Which way is the ball accelerating? Same way, right? So if the ball is accelerating this way, right? That means it has to experience a force that way, right? So right now, there's two forces acting on the ball, correct? Right? That's what happens here. So really, this acceleration, even though the ball was rolling, the ball rolling is a result of the force of friction between the ball and the surface of the clipboard. The reason why the ball was rolling this way was really because the acceleration was 0. The ball was staying in the same spot. Right? Do I need to do it again? Can we do it again? Okay. Watch the ball. Alright? Take my thumb out of the way. Thumb, get out of the way. Okay. Watch the ball. Can I see the ball? Okay. As I walk, the ball's trying to stay in this spot. It's as if I'm walking and the ball's staying right there. Now it rolls because there's friction between the ball and the surface. Okay? But the ball's trying to stay right there. I wish I was talented enough so I could hold my finger this way and walk that way and have my finger stay here, but I can't do that. Okay, let's try. No, not really. Okay, you guys see it though? Okay, the ball's trying to stay right here relative to the room. All right? If the room was an XY axis or an XY coordinate plane, and every spot had an X and Y coordinate, the ball's X and Y coordinates would stay the same, but mine would change. Okay, does that make sense? So really it has no acceleration. Now when I flip the clipboard around, right, and I walk that way, the ball moves with me, doesn't it? Because the clip applies a force. So the ball accelerates in the same direction that I do. Does that make sense? Okay. The same thing can be said for me as I'm walking with the ball. Okay. So I'm walking this way and I stop. Right? The ball wants to keep in motion, wants to keep moving, right? So it rolls off my tray. Does that make sense?
Yeah.
Yeah. Does it really, or is that just... Okay. So, in this situation, these are my two forces acting. That's why we can't say unless the force is exerted, Moses, because there's two forces exerted right here. Okay? These two forces are acting in this case, right? Now, when I add the blue force, just like this one, the clip applies an outside force on the ball. Okay? And that outside force is what causes the ball to accelerate in the same direction as the clip. Does that make sense, guys? Does that make sense? Yeah. Okay. Another cool demo. I've never tried it with a big cup like I have right here and a larger magnet. I usually use the penny. I think this is gonna work from the get-go. If I flip the paper clip out, if I flip the note card out, what's gonna happen with the magnet? Should fall in the cup, right? Let's see what happens. Okay. Where'd the magnet go?
Wait, that's a good question.
In the cup. Why'd that happen?
Because it wants to stay at rest. It's not.
Yeah.
No force being applied directly to the magnet.
Good job, Sergio. The magnet wants to stay at rest. The magnet wants to stay right there, right? So if I don't apply a force to the magnet, okay, if I don't apply a force to the magnet, I hit the cup. Okay. If I don't apply a force to the magnet stays right there. Does that make sense, guys?
Oh, it's like the table trick where you try to like.
That's exactly it.
Oh, like when you take off the cloth.
I never.
You know what? You know when a magician does the table trick? Everybody know what I'm talking about?
Yeah.
Where they yank I'll find a video for tomorrow then. Okay. Where they yank the tablecloth out from the table. Okay. Now, do they ever yank them towards you, or do they yank the tablecloth towards you or away from you?
I wouldn't know. I always feel like.
They always yank it towards you. Okay. Because they set the trick up so that the tablecloth, the edge of the tablecloth, is on the edge of the table. Right. So that way there's no tablecloth hanging over the other side. So that when they yank out completely horizontally, it's just like the note card underneath the magnet. Okay? The note card goes completely horizontal, and the magnet falls down because it wants to stay at rest. Right. Same thing happens with the table trick. So if you're having trouble with the table trick, try moving your tablecloth so it's on the edge of the table, so it doesn't have to come up and over. It just has to go horizontal. All right?
Should I do it on the big table? Or is that
I'm not going to advise you to do it anywhere because I don't want to be responsible for when you break your mom's dishes. All right?
Or plastic?
Well, the plastic ones have a lot smaller mass. Okay, so this quantity that we're going to talk about here in a second is a lot smaller, so they're easier to move. Okay? There's a reason why I chose the baseball instead of a tennis ball for my clipboard trick. Okay, does anyone know what the reason is? Bigger mass, right? Does it take more force or less force to move the baseball? It takes more force, right? That's why the table trick doesn't really work with solo cups and plastic plates. Okay? That's why they need to use the heavy dishes.
So the dangerous ones.
Okay? The ones that are easier to break.
There is no practice.
Nope. You gotta do it right the first time. Okay? So, does anyone know that quantity that the bigger mass object has that the smaller mass object might not have that is very important here? It begins with an I. You may have heard it before. What is it? Inertia. What is inertia, Nakira? Richard?
It's like the force required to get an object moving, right?
Isn't it like the resistance?
Not really, but close.
Isn't it the resistance?
I forgot. They always had it on
Resistance.
some
Resistance.
motion.
It's a resistance to what?
Motion.
Not force.
Motion.
You're right, Sergio. It's resistance to... See if I'm going to go 0 for 3 today.
Oh, the flag.
Flag. Blaming flag. Flag on the play. Thanks, Julian. Okay, inertia. Inertia is an object's resistance to a change in motion. Okay. Or an object's, sorry, I'm going to change it just a bit. An object's tendency to resist. Sorry about that. That's okay. Tendency to resist a change in motion. Now, a lot of people get this confused with mass. Okay. Why do you think people get this confused with mass? Richard?
Because the heavier something is, the harder it is to move.
The heavier something is, the harder it is to move. That's exactly right. Okay. Heavier objects have more inertia, and they also have more mass, right? So people tend to think that mass and inertia are the same thing, but they're not. Okay. Larger objects have more inertia. Smaller objects have less. Right? Objects that have more matter have more mass. Right? So larger objects that have more matter have more mass and therefore have more inertia. But they're not the same thing. Okay? Inertia is an object's tendency to resist the change in motion. Mass is the amount of matter that an object is made of. You guys see the difference? You guys see the difference? Draw a picture of it? Well, it's hard to draw a picture of matter because I don't want to draw those atoms. Right? Well, think about this baseball. Right? If the baseball is stationary, if the baseball is moving, does it have the same amount of mass?
Yes.
Yeah. Okay. Does it have the same amount of inertia? Yes. Okay. The baseball still needs the same amount of force applied to it to accelerate at 1 meter per second, whether it's stationary or moving. So if the baseball is stationary right here, and I want to accelerate at 1 meter per second that way, I have to apply the same amount of force as if the baseball is moving, and I want to accelerate at 1 meter per second that way. Okay? Does that make sense? All right. Now the inertia is the baseball's resistance to that change in motion, resistance to its change in acceleration. Where the mass, Richard, is just how much stuff it's made of. Okay. Does that help at all or no? Yeah? Okay. So, inertia is not mass, but is directly related to mass. Directly related to mass. Okay.
How does that work with round objects?
What do you mean?
Isn't it easier to move 10-pound ball than a 10-pound box?
Yes. Good question. Remember the other day we talked about centers of mass?
Was I here for that?
You might not have been. Okay. Think about a round object. The center of mass is right there, right? Now, if I want to get something to roll, I want to get the center of mass out over the edge of it. If I look at a round object, its edge is really right below it because it only has one contact point with the surface, right? So if I can get the center of mass to just move just a little bit, just a little tiny bit that way, then it'll start to roll. Okay? If I have a block, okay, I have to move the center of mass a lot to get it out over the edge to get it to roll. Okay? And then it comes down to a difference between rolling friction and sliding friction. Okay? The rolling friction of an object, and we'll get into this later, is a much smaller amount than the sliding friction. So if the ball rolls, it will have a much smaller friction than if I were to have it slide. Okay, if I push the ball along the surface, then the surface exerts more friction than if I let the ball roll. Okay, does that make sense? Okay, that's why our cars have tires that roll versus tires that are stationary. And that's why when you hit the brakes in your car, you slow down because now you're telling your tires they have to be stationary for a moment. Okay, because that sliding friction is greater than the rolling friction. Does that kind of answer it without getting too in depth? All right, any other questions about inertia? There's something else that's going to add, but I can't remember what it was. Oh, inertia is not a force. Okay. It's not a force. Okay. Now, because of this idea of inertia, this first law is sometimes called the inertial law. law. It's called the inertial law. All right. Are there any questions about Newton's first law? Any other questions? No?